Hello everyone, and welcome to our presentation. Today we will delve into a research paper on high-performance routers. The title is a 50 GB per second IP router. This paper discusses the design and implementation of an IP router, MGR, capable of processing tens of millions of packets per second and achieving a speed of up to 50 GB per second. The design of this router aims to address the performance bottlenecks of existing routers in high-speed network environments. Our presentation will cover various aspects, including the background, design goals, architectural innovations, and the performance characters. Let me first explore why such a high-speed router is needed. At the beginning, starting with introduction and background, with the rapid development of network technology, link bandwidth has been steadily increasing. For instance, between 1996 and 1997, the number of Internet service provider customers and the bandwidth usage grew significantly, which created higher demands on routers. Traditional routers often became performance bottlenecks and couldn't keep up with the increasing bandwidth. Therefore, this study aimed to develop a router capable of handling link speeds of up to 50 GB per second to meet the latest network demands. High bandwidth requirements are not just limited to core networks, but are increasingly vital in data centers and wireless networks. For example, we found a paper, a scalable community data center network architecture. It highlights the importance of efficient router designs in handling the growing demands of cloud service. Similarly, another paper, CSMACA performance under high traffic, demonstrates how wireless network environments can exacerbate router bottlenecks and heavy traffic, which make innovations like MGR essential. Next, let's talk about MGR router design objectives. The research team set three primary goals while designing the MGR router. Multi-gigabit internal bandwidth. It is the ability to transfer packets between different interfaces and multi-gigabit per second rates. High packet processing power. This needs to process millions of packets per second to meet the requirements of high bandwidth links. And for protocol standard compliance, the router must conform to IPv4 router requirements to ensure compatibility in existing network environments. Additionally, as highlighted in routing policies in ISP networks, demonstrate ISP specific policies and strategies is crucial to ensure efficient packet handling for diverse routing scenarios. And the third part, about MGR router architecture. The architecture of the MGR router is unique, comprising multiple line cards, forwarding engines, and a high-speed switch. These components are connected via the switch, forming an efficient distributed system. Line cards are responsible for receiving and transmitting packets, while forwarding engines make routing decisions for the packets. The switch facilitates data transfer between these components. Unlike traditional centralized routing tables, each forwarding engine in the MGR router maintains a complete routing table. Avoid the central routing table become a bottleneck under high loads. Then for MGR router innovations, the MGR router introduced three major innovations. First, separation of engines and line cards. Traditionally, forwarding processes are integrated into line cards MGR separates them, improving flexibility and avoid the limitation of interface speeds by the processor performance. And switch the backplane efficiency. It means shared buses often become performance bottlenecks, whereas the switched backplane provides higher parallel processing capabilities that enhance packet processing efficiency. And for third one, complete routing tables in engines. This design limits delays caused by accessing a central routing table under high traffic conditions, which enhance overall router efficiency. So, the inclusion of QoS functionality aligns with the principles of random early detection gateways for congestion avoidance, which emphasizes managing traffic to prevent congestion well. Now, my partner Haojun will go through the rest parts.
Okay, let me explain the performance of this router in the article. At the heart of this router is forwarding engines. Each one uses an Alpha 21164 processor, which allows the routers to handle 32 million per second packets per second and support a backplane at 50 gigabytes per second. This is a big step up from older designs. The router also uses a routing cache to store recently used destinations. This step speeds up package forwarding since many packages in a flow share the same destination. However, as a study low latency distributed downlink for low Earth orbit satellites says, there's a potential for even more optimization with low latency routing methods. Besides, let's move to the role of the network processor. The network processor is like the router's brains. It's a commercial PC motherboard that handles routing updates and manages the whole system. It also runs all the routing protocols and signals the forwarding engine with updating routing tables. What's smart here is how this router separates routing updates from forwarding table updates. This prevents issues like router flapping from slowing down package forwarding. This idea is supported by analysis of increase and decrease algorithms for congestion avoidance in computer networks, which shows how decoupling process can lead to more stable and efficient systems. In conclusion, to wrap these things up, the router proves that router technology can keep up with today's high-speed networks. It's packaged with innovation that solves the performance problems of older designs and paves the way for further improvements. Looking ahead, as network grows and evolve, design like these routers will need to update too. Papers like IPv6, which is the Internet Protocol next generation, reminded us that future routers must also support next generation protocols and even higher bandwidth demands. That's all for our presentation. Thank you for watching this video.